Yeah, can you see my presentation?
Yeah. Hello, Andrei. We can see your presentation. How are you today?
Fine.
Yeah, that's good. So, Andrei will be presenting on the research of the relationships between algorithm complexity and gas consumption by sorting algorithm in smart contracts. Andrei, the stage is yours. Yeah,
Thank
we're
you.
happy to have you with us.
Thank you. Ladies and gentlemen, good day. My name is Andrei Parasar. As it was mentioned, representing the Odessa National Polytechnic University. Today, I will share the results of our research, focusing on the relationship between algorithmic complexity and gas consumption in sorting algorithms within smart contracts. So, Okay, let's begin with a brief introduction. Today we will discuss this here on this forum, blockchain, smart contracts, and their significance in the modern world. Blockchain technology has transformed how the world perceives data and found applications in various sectors, including finance, logistics, and even art. More, we are introduced to the smart contracts, a key element of the blockchain ecosystem. Smart contracts are programs capable of automating and ensuring secure agreement execution between participants without the need for intermediaries. So one of the leading technologies to explore is the Ethereum platform and the concept of gas. Ethereum is a decentralized blockchain platform that distinguishes itself from Bitcoin by enabling the creation of smart contracts and decentralized applications. Gas is a vital concept determining the cost and security of transactions and smart contracts on this platform. Each transaction and smart contract has a gas limit, restricting the maximum amount of gas that can be used. This is essential to prevent abuse and ensure predictability in network operations. This concept of gas plays a crucial role in optimizing resource consumption on the Ethereum network. So about algorithmic complexity, we should say a few words. Algorithmic complexity assesses how quickly and how much memory an algorithm requires for execution. There is a mathematical method developed by Donald Knuth in the middle of 20th century. This method allows abstraction from specific system characteristics and provides tools to evaluate the efficiency of algorithms. One of these tools is the analysis of execution time and memory usage using metrics such as the number of basis operations required to execute the algorithm. This approach helps compare algorithms independently of specific hardware. Sorting algorithm overview. So sorting of array is a common task that requires organizing an input data set into a specific order. When we're analyzing the efficiency of sorting algorithms, we use the BICO notation, also developed by Donald Knuth, and it follows the same principles as it was mentioned earlier. So, paper motivation. The question is not what is the catch. The right question is there a catch in principle? Is there it in principle? The essence is that we have two criteria for assessing an algorithm. The first is mathematical, more theoretical, representing an abstract theoretical assessment. The second one is practical. When we are comparing gas consumption, we see which solution is better for a specific task. Based on all the aforementioned, we want to understand how the practical aspect of gas consumption relates to the mathematical complexity assessment of an algorithm. To achieve this, we analyze various sorting algorithms and their gas consumption, as well as investigate how changes in input data size affect gas consumption during sorting. With that in mind, I invite you to review a table describing the algorithmic complexity of each of the selected sorting algorithms. In total, it was selected 6 well-known sorting algorithms. These include those with quadratic complexity like bubble sort, selection sort, insertion sort, as well as more time-efficient ones like merge sort, quick sort, and also counting sort holds a unique position since its evaluation depends not only on the size of the input data, but also on the range of the largest element. Implementation equality. So on this slide, we delve into a crucial concept, implementation equality within the concept of blockchain, for example, such as Ethereum. Firstly, this concept revolves around the idea that when developing and implementing algorithms using smart contracts on the blockchain, all algorithms should yield the same results with identical input data and execution logic. However, there is a more critical aspect embedded in this notion. To grasp it fully, let me show you some examples. Example number one. So there are two data structures that play significant role in the development of smart contracts on the Ethereum platform. It's mapping and arrays. Mapping is a special data structure that establishes a correspondence between keys and values. It employs a hash table under hood for swift data accessed by key. On the other hand, we have an array. It's usual array, an ordered collection of values of the same data type. Based on the results shown in the table, when we don't iterate through elements using a mapping with a hash table, using hash tables generally is more gas efficient compared to an array. Example number two. The Ethereum virtual machine, EVM, is responsible for storing and managing persistent data in the context of smart contracts. It consists like 2 powered 256 slots, each containing 32 bytes of data. So when we initializing the smart contract, the EVM writes each variable to storage in the order they are declared. However, this organization can lead to inefficient use of storage slots. In this example, we can see that semantically, the variables are the same in both cases. However, looking at the table, which demonstrates the gas consumption from both approaches, it's evident that a more efficient approach in terms of scalability and gas usage is to arrange variables so they fit into fewer slots. This allows for more efficient resource utilization and gas savings. And the last one, example number 3. In Solidity, there are two places to store data, memory and storage. Memory is temporary storage used only during function execution. In contrast, storage is permanent storage, where data is preserved between function calls and transactions. It's worth mentioning the existence of opcodes, also known as operation codes, which are mnemonic representation of instructions executed by the EVM during smart contract execution. These are basic commands that define what a particular operation does. As we can see, there is a difference in gas consumption between operations related to memory and to storage. Reading and writing to memory, it's mload and mstore, cost 3 gas. Operations related to storage are obviously more expensive. For gas optimization, it makes sense to write variables in the function's scope to memory area and then access them inexpensively. So now I guess we can return for a second for implementation equality. As we have seen, different ways of writing code can optimize gas consumption in different ways. However, this was demonstrated not to dictate you how to write code, but rather how not to write it. What I mean that implementation equality means that the optimization approach or method used for one algorithm is obligatory when applied to another algorithm. if we aim to achieve fairness and transparency in our research. And this happens that in our research, it was used. We used implementation equality. So if we used, for example, something as return time type of one sorting function, it was used in all other ones. Summing up, to analyze gas consumption, we employed the following method. We created 50 lists with 100, 500, and 1000 elements for each of the discussed sorting algorithms. Then we computed the average gas consumption for each case. As a result, we can present the findings of our study in the form of a table and make conclusions about the impact of algorithmic complexity and gas consumption. While sorting, while bubble sorting, selection sort, insertion sort have constant space complexity, quadratic time complexity significantly affects actual gas consumption. With a small number of elements, the difference may not be noticeable. However, as the number of elements increases, gas consumption sharply rises, confirming that quadratic algorithms are not an efficient choice for blockchain sorting. The gas consumption for bubble sort and insertion sort is so high that considering them from 100 elements in more is impractical. Merge sort and quick sort exhibit notably economical gas consumption. This implies that the degradation in space complexity from constant to linear or logarithmic one is not as significant as the improvement in time complexity from quadratic to O(n) log n. It's worth noting that quick sort still yields better results since it has better space complexity with the same time complexity as merge sort. Counting sort holds a special place, as it was mentioned, because its complexity depends not only on the size of the input data, but also on the range between the minimum and the maximum elements. When this range is not large, difference between minimum and maximum, this algorithm becomes the most efficient among those considered. However, as the range increases, its obvious gas consumption also rises, making the choice of this algorithm extremely cautious. In conclusion, our calculations make it clear that gas consumption in the blockchain is directly linked to the algorithmic complexity of sorting algorithm. It's important to know that due to the specific of gas consumption in the blockchain, it's impossible to consider only temporal or spatial costs, since gas is charged for comparison operations, calculations, and memory allocation, and necessary for algorithm execution. Therefore, both aspects must be taken into account. So finally, we are on the last slide. So I invite you to ask questions and initiate a discussion about research.
Andrei, thank you so much for the very good presentation. It is definitely interesting, and I can say I personally would return to reviewing it and to reading the paper. I think the good angle in asking the question will be, so basically, yeah, these sorting algorithms, they can be there are a wide range of cases where they could be implemented. But can you provide, for example, like some simple example? So, for example, as a result of this work and using the conclusion of this work, the use case, and then you provide the use case, can be improved. So, what is the use case?
What is your use case of all this paper?
No, the use case, for example, the application. So basically, you apply it to what? What is what can be optimized?
Okay, the first thing that if you need sorting algorithm, for example, you should understand that you should not rely only on time complexity, but on both. And I think it's the most important angle generally, because it gives us an opportunity not rely on sorting algorithm at all. So yes, in this paper, sorting algorithm was chosen, but it doesn't mean that it's the only approach we should consider to research. We can choose any algorithms and keep this angle of understanding that some mathematical ways of our evaluation of algorithm that we used in Web 2 can not be applied in Web 3. Or they can be, but we must check it. Because here I checked and we still can use it, but we don't know. Maybe in some other cases we can't use, for example, time and memory complexity. So it's still, so that's my point.
Understood. You were talking you were talking about reducing the gas consumption, right?
Yes.
So gas consumption in which use case? So basically, is it a use case for regular transactions, or is it a use case for some execution of smart contract, or so basically, where are we getting the advantage?
In my opinion, first of all, for transactions, because they are broadcasting to all nodes, so less gas consumption at this moment of work of blockchain is one of the most important one, because because we have U and P functions, and generally we can execute something on local nodes. And it not depends on which sorting algorithm we use. That's why here I don't review it, because it always it's all efficient, and it's all goes to understanding that quicksort is the best one. So it's not the case. So in my opinion, the transaction point, because of its execution on all nodes, is the most important one when we talk about less gas consumption.
Okay, understood. Thank you so much. These are all questions on my end. I don't see right now our audience asking other questions. So, Andrei, it was great having you on the stage. Thank you so much for joining us. And we will return back to your paper, and maybe you can expect us sending you some clarification question.
Thank you.
Thank you. Have a good day.